The figure above shows 3 parallel wires in the plane of the page that each carry a current I. 3 points near the wires, J, K, and L, are also labeled. The wires and label points are equally spaced a distance d apart as shown. Indicate the direction of the magnetic field at point K due to each of wires 2 and 3 separately. Describe how you arrived at your answer. All right, the field around a long straight wire is going to be, let's go over here and just sketch it quickly, is take the right-hand rule says that curl your fingers around the current. So let's say the current's going like this. And we get a circular field, which, as drawn here, put my thumb on the current, has come out of the board here and into the board here. So looking at wire 2, at point K, it's out of the board. Of course, if we do the same sort of thing but flip the direction for wire 3, then it's going to be into the board. In a clear, coherent paragraph length response, rank the magnitudes of the net magnetic field at points J, K, and L due to the 3 wires. Use physics principles to justify your answer. And again, as I've said in other ones, don't use magic wishing stones. Use physics. So we're going to start off by saying let's say that there's a fundamental unit of field which is what's felt one distance away. So if we're at a distance d from the wire I, we get a field of strength of B0. For concreteness, let's also take that a field out of the page is positive. So so this, is positive field, and this is negative field. So if we look at the field at, say, J, we're going to gain, since we're going around that wire, it's coming out from wire 1, so we gain 1 B0. And since wire 2 is in the same direction, we're going to gain whatever wire 2 is, but it is 1, 2, 3 times further away, so it's 1/3 B0. And then we're going to lose whatever wire 3 contains, but that's only 1/5 B0. Or the incredibly obvious 17/15 B0. Okay. Let's go out here and say, what about B from K? B at point K. Well, now we're going to lose B0, right? Not lose, but it goes into there. But we get back the same from wire 2. And then we lose 1/3 B0. So that is minus 1/3 B0. And then at L, we are in the negative direction, right? We're below this axis, so we're below wire 1, so we get minus, but we're 1, 2, 3 away, so minus 1/3 B0. We're below wire 2, and so we're going to lose that as well, and it's only one thing. And then we're going to gain B0 because we're also 1 unit away. And it's coming, in this case, it is going into the board, so actually also minus, which turns out to be minus 7/3. So we only care about magnitudes, so we would have that BL is more than BJ, which is more than BK. This is what I call a brute force approach, just finding the fields and comparing them. You could probably reason out by saying something like, at point L, all 3 fields point in the same direction, so they will be maximized. That will be our largest. And that at point K, the fields from 1 and 2 cancel, leaving only a field from 3, which would be therefore the least, and that J has to lie between them. Although I think the brute force method in this case was probably a little safer. Wires 2 and 3 are removed, and a uniform electric field is created in the region around wire 1. A negatively charged particle now moves parallel to the wire with a constant speed towards the right along the line through point K. What is the direction of the electric field, and justify your answer. So our key bit here is the insight that it moves with constant speed. That tells us the net force is 0. Now, as we discovered before on the other page, since we are below this current, the field is into the board, and we know that the magnetic force is QV cross B. So let's figure out where that would be. Well, we have, if this is our coordinate frame, and we have a velocity which is moving that way, and a magnetic field which we just said was into the board that way. So this direction is V cross B. But notice that we have a negative charge as well. So the actual force due to magnetism is this way. So if I draw my free body diagram, the magnetic force is actually deflecting this thing downward. If it's going to not move downward, then there must be an electric force which is pointing upward. So the electric force is up. But the electric force is Q times the field, meaning, or put it this way, electrons move opposite to the field, so an electric force pointing up means the electric field must also point down, as does the B field. As an interesting aside, had the charges been positive, had this been a proton moving this way, then all the forces would flip sense, but they would both flip sense. So in other words, the electric field and the magnetic field would have to be in the same direction, no matter what the charge is.